Something is wrong with reality. For a century, quantum physics has told us something deeply uncomfortable. Reality does not always behave like reality should. Particles can act like waves. Two objects can share a quantum state across enormous distances. And in the strangest experiments, nature refuses to behave as though objects carry definite properties before we measure them. But something has changed recently. Physicists are no longer testing these ideas only with individual photons or tiny particles. They are pushing quantum behavior into larger systems, more complex experiments, and increasingly precise measurements. And the results are making one question harder to avoid. What exactly is reality doing when nobody is looking? In 2026, researchers demonstrated quantum interference using sodium nanoparticles containing more than 7,000 atoms each. These were not single electrons or isolated photons. The particles were massive enough to behave in a distinctly quantum way while moving through an interference experiment, creating what physicists describe as a macroscopic quantum, or CAT state. The surprising part is not simply that quantum mechanics survived another test. It is how far the strange behavior can extend. Imagine throwing a tiny metal cluster through an experiment and giving it two possible paths. Classically, you would expect the object to choose one path, but quantum mechanics describes something different. Before measurement, the system can behave as though both possibilities contribute to the final outcome. When those possibilities overlap, they interfere, producing a pattern that cannot be explained by imagining an ordinary object secretly taking one route. For decades, physicists have performed versions of this experiment with increasingly large objects. Now, the boundary is moving. The quantum world is beginning to look less like an isolated microscopic realm and more like something that can survive at scales approaching the everyday world. But there is an even stranger problem. Quantum theory doesn't merely produce unusual interference. It produces correlations that seem to resist our ordinary ideas about distance and cause. In 2025, experiments continued to test Bell's inequality, a mathematical boundary separating ordinary local hidden variable explanations from the predictions of quantum mechanics. And the result has repeatedly been the same. Under carefully controlled conditions, quantum systems violate the classical limit. And newer experiments are pushing that phenomenon into different physical systems. Researchers have observed Bell correlations in momentum-entangled ultra-cold helium atoms, showing that even the motion of massive atoms can participate in these deeply non-classical correlations. Then, in 2026, a quantum repeater experiment distributed entanglement between two solid-state quantum memories separated by 14.5 kilometers and produced a measurable violation of a Bell inequality. That matters because the experiment was not simply creating an abstract quantum state. It was demonstrating non-local quantum correlations across a metropolitan-scale distance. So what are we supposed to make of this? It does not mean information is traveling faster than light. It does not prove that human consciousness creates reality. And it does not mean physicists have discovered that the universe is literally an illusion. What the experiments actually show is more precise and perhaps more unsettling. The universe does not appear to obey the classical picture in which every object carries a complete set of predetermined properties, independent of how measurements are arranged. Quantum mechanics keeps passing tests that classical intuition cannot. And now, scientists are asking an even deeper question. If quantum behavior can survive in larger objects, across greater distances, and inside increasingly sophisticated machines, where does the quantum world actually end?
That question becomes even stranger when we stop looking at isolated particles and start looking at matter itself. One of the newest clues comes from a material that at first glance looks completely ordinary. Researchers studying a centimeter-sized crystal of a so-called strange metal found evidence of a high degree of multipartite quantum entanglement spread throughout the material. They did not create a giant object that was literally in two places at once. Instead, they found that groups of quantum components inside the material were behaving collectively in a way that could not be explained by treating them as independent particles. The analysis indicated that at least 9 quantum entities were acting together as an entangled system. That distinction matters. Quantum mechanics may not simply describe tiny objects. It can also describe collective behavior emerging from enormous numbers of interacting particles. And this creates a completely different picture of reality. A solid object on your desk appears classical because its microscopic quantum behavior is constantly interacting with its environment. Those interactions destroy delicate quantum coherence extremely quickly. But underneath that apparently ordinary surface, quantum correlations can still exist. The classical world, therefore, may be less like a separate layer of reality, and more like what emerges when quantum behavior becomes too complicated and too connected to its surroundings to remain visibly strange. And scientists are now finding ways to control some of that complexity. In 2026, researchers demonstrated quantum teleportation with an efficiency advantage over directly transmitting single photons through a lossy channel. The experiment does not teleport matter, and it does not send usable information faster than light. Instead, it transfers an unknown quantum state using shared entanglement and a classical communication step. This sounds almost impossible until you remember what quantum entanglement actually means. The information describing a quantum system does not always belong neatly to one object. Sometimes it is encoded in the relationship between objects. That relationship can then become a resource. And that may be one of the most important lessons from modern quantum physics. The weirdness is not merely an obstacle scientists are trying to eliminate. They are learning how to use it. Quantum computers, quantum networks, and quantum sensors all depend on controlling phenomena that classical physics cannot reproduce. But there is still a boundary nobody has completely explained. Why does the quantum world look so different from the world we experience? The answer may involve decoherence, the interaction between quantum systems and their environments. But decoherence explains why quantum interference becomes difficult to observe. It does not, by itself, settle every philosophical question about what a quantum state means. And this is where the mystery survives. Some physicists investigate interpretations in which all possible outcomes have a physical role. Others explore theories in which the quantum state represents information rather than a literal physical object. Still others search for tiny deviations from standard quantum mechanics that could reveal new physics. So far, experiments have not delivered a confirmed replacement for quantum theory. Instead, they have done something more frustrating. They have made the theory harder and harder to dismiss. From quantum tunneling in electrical circuits large enough to study as macroscopic systems, to matter wave interference with nanoparticles, to entanglement inside materials and across long distances, the same strange framework keeps surviving increasingly demanding tests. The result is that scientists have discovered reality is an illusion. It's almost the opposite. Reality is real, but our everyday picture of what real means may be incomplete. At the smallest scales, nature does not appear to behave like tiny billiard balls moving through an invisible machine. It behaves according to rules that connect possibilities, measurements, information, and physical systems in ways our intuition was never built to understand. And perhaps that's the most important discovery of all. The deeper scientists look, the less quantum physics looks like a strange exception to ordinary reality. It increasingly looks like the foundation underneath it. So the mystery is no longer whether quantum mechanics is strange. We already know it is. The deeper question is this: if the familiar world is built from quantum rules, why does reality look classical to us at all?